Okay, so this is the lesson where all of the probability knowledge that we've kind of been developing throughout this unit comes together, and we actually use it to make some claims and draw some conclusions about data sets. We did this a little bit on the first day of the probability unit. We were just playing around with some results that we got in class. I think we were dealing with like cats and dogs and whether or not you have older siblings. So what we're going to do here is prove whether or not two events are independent of one another. And we're going to do this using conditional probability. So this is one of my favorite things in the school curriculum because I feel like it's a real world applicable thing where you can do studies like this all the time and figure out if things are true based on data. So I think that having siblings is not dependent on whether or not you're a sophomore, meaning, and logically I think this probably makes sense to all of us, it's not more likely that you have siblings just because you're a sophomore. Being a sophomore does not determine whether or not you have siblings, right? And I think this because everyone's a sophomore at some point. There's no distinction between people with siblings becoming sophomores or being sophomores and not having siblings. There is nothing there. So I think that these two things are not related at all. But I want to prove that. So what I'm going to do is I'm going to conduct a study and see if this is actually true. Unfortunately, we're not in person. It's hard for us to do these studies like we would have done in class. So I'm just going to use the data from last year. And when we do get back to class, we might do some things like this so that we can remember how to do this and do some fun activities involving these skills. So I'm going to draw a two-way table here. This is commonly how data is presented. We've seen a few of these on Delta Math and in some quizzes and lessons so far. These and Venn diagrams are pretty much the two ways that you should try to demonstrate data as long as it's not consecutive events. So we've got siblings and we've got not siblings, the complement of siblings, and we've got sophomore, I'm going to use P, and not a sophomore. Okay, so let's think about what's going to happen here. If I'm right and these two things are not related at all, then what I'm saying is that the probability of having siblings should be the exact same if I'm picking from the whole group as it is if I'm pulling from people who are sophomores. Right? So what I'm saying is the probability of someone having siblings in this class should be the same as the probability of someone having siblings in this class given that they're a sophomore. These two things should be the same. If they are, then I've proven that they are totally independent, not dependent on one another. So I'm just going to use the data from last year and populate this table real quick. So you'll probably remember from previous lessons where I used this data. This class has 20 kids in it. I'm just going to put that total number 20 there. It's not a bad thing to keep track of. And I'm going to add the totals of sophomores. So we have 3 plus 4. We have 7 sophomores. That's a good number to have on hand. And it looks like we have 13 students who aren't sophomores. We have 9 students who have siblings, and we have 11 students who don't. So it's good to have these totals available to us. So again, what I'm trying to prove is that the probability that someone in this class has siblings is the same whether we're picking from the whole class or whether we're picking from only sophomores. And if that's true, then I can say that having siblings does not depend on whether or not you're a sophomore. So let's conduct this here. What's the probability of someone having siblings in this class? Well, there are 9 students in this class that have siblings out of 20. So 9/20ths is the probability that someone has siblings. And we should recall our conditional probability formula here. I should use blue. That's kind of jarring on a white background. So we want the probability of sophomore as our denominator and the probability of the intersection of siblings and sophomore in our numerator. All right, so how many sophomores are there? There are 7. And of those 7 sophomores, how many of them are both sophomores and have siblings? 3. So I want to compare these. They don't have the same denominator. I could try to get a common denominator, but I think what I'm going to do is just type these into a calculator and get them as a decimal, because that's going to be enough to prove if they are equal. So when I do 9 divided by 20, I get 0.45. And when I do 3 divided by 7, I get 0.42, approximately 0.43. So this is a small set of data. But what I've shown here is that you are more likely to have siblings if I'm picking from the whole group than you are if I'm only picking from sophomores. So my data actually says that these are dependent on one another because these aren't equal. It's not true that you're just as likely to have siblings regardless of whether or not you're a sophomore, because the probability of you having siblings is 0.45 if I pick from a whole group of people, and if I pick from only people who are sophomores, that probability goes down. So my conclusion here would be that these are not independent. Now this is just 20 kids from a year ago, and it's a small sample size, and these percentages are pretty close. So you might find that if we did this over the entire population of the world, then these would be the same percentage because you'd have enough data at that point. And I think you probably would, because data would show that having a person be a sophomore does not have anything to do with whether or not they have siblings. But unfortunately in this group, we did have a difference in those numbers. So this is how we're going to prove if two events are independent. And generally, I'm just going to make some statements here. So to prove independence, we can do what we just did and say, let's see if the probability of some event A is the same on its own as it is if it's given that there's another event B. If those are the same, then they're independent. It would be just as doable and just as valid to prove the opposite, that the probability of B is equal to the probability of B given A. That's the same thing. So we could prove that. Now just for a second, I'm going to investigate this probability of A given B formula. And remember that that really is the probability of A intersection B divided by the probability of B. So just for a minute, let's rewrite this formula. All right, I'll keep using blue here. I'll take this whole formula, the probability of A equals the probability of A given B, and replace it. Right, so I'm just putting that there. So I've rewritten this formula, but instead of writing the probability of A given B, I've used its definition instead. And I'm going to do a little algebra here and rework this times the probability of B times the probability of B. And I end up with the probability of A times the probability of B equals the probability of A intersection B. If this is true, you've proven independence as well, because that just came from this independence formula. So essentially, if you can prove any one of these things, and you don't have to do all three because they really are all the same formula, just rewritten in different ways, any of these proves that two events are either independent or not independent. And so we'll use a couple different ones here in this last example. So the following study details the favorite subjects of a sample of high school students. Determine whether a student choosing English is their favorite subject depending on them being female. So this is just a table of data pulled off the internet, random assortment of numbers, and we're going to prove based on this data if this claim is true. So the way that we're going to do that is, and I'm going to say that E is English and F is female. Based on these numbers, I want to either prove that the probability of being female is the same regardless of if I pull from the whole group or if I just pull from people who chose English. So that's one way that I could do this, and you could think of that as this example of using our probability formula. I could reverse this, and that would show the exact same thing. So I could show that the probability of someone choosing English is the same regardless of if I pull from the whole group or if I only pull from females. So that's this version of the formula. And again, you don't have to do both. You can just do either one because they will show you the same information. Or finally, I could show that the probability of someone being a female out of the whole group times the probability of someone choosing English out of the whole group equals the probability of someone being a female and choosing English. So that's this version of the formula. Any one of these three will work. You don't have to do them all. So whichever one you're most comfortable with. And let's prove them here pretty quickly. We can plug in this data. Okay, so I'm just going to go down the line. What's the probability that someone's a female? Well, it looks like there are 30 out of 57. So 30 out of 57. the probability that someone chooses English, there are 10 people who chose English out of 57. And where are the people who are female and chose English? Okay, so that's these 6 out of 57. All right, so we'll do the multiplication there. If I round to the hundredths place, I get approximately 0.09 equals 0.11, and those are not the same. So because those aren't the same, I've proven that these are not independent. And I'm just going to show you now that these other formulas would have given you the same result. So I've just filled in the values. Probability of female is still 30/57. The probability of female given that a person chose English is 6 out of the 10 people who chose English. And then over here I've got the probability that someone chose English, which we already said was 10/57. And this is the probability that someone chooses English given that they are a female. So of the 30 females, how many also chose English? I'm going to convert these into decimals, and then we'll be able to make our final conclusion. So when we convert these into decimals, we see that none of these statements are true. And so this is why I'm saying you don't have to do all 3 of these. Any one of these is enough to prove whether or not 2 events are independent, because although these didn't all come out to be the same values in every equation, the important thing is that they all were not equal. So this statement was untrue, this statement was untrue, this statement was untrue. If this statement had been true, these would have also been true. So based on these results, because these 2 things are not equal, we can say, therefore, the probability that a student is female, and I'm going to abbreviate, is not independent of the probability of someone liking English. So it seems, based on these results, and they're still very close. So again, this is maybe an indicator that if we broaden the study and sampled more than just 57 people, we might eventually find that these are independent, and probably would. But based on these results, it looks like choosing English as your favorite subject and being female are not 2 things that are independent of one another.